So let me just first do a very quick recap of what we have done in this particular lecture topic. And then we will add a few more things. Okay, so we have been looking at this beamforming / temporal filter, either the spatial filter or the temporal filter signal model, where there is some vector x that has been received, and it can be modeled as a linear transformation of some vector s of interest. This is our, for example, our symbol vector, after it is transformed by this matrix W, and maybe there is some noise component present as well. Okay, so that is the general model that we have seen. We have been looking at the correlation matrix of that linear transformation W. R is defined as W transpose W. And we have seen that with that, we can kind of form what is known as the sufficient statistic vector Y, which is obtained by projecting the vector X onto different columns of this W matrix. Okay, and so the resultant vector Y, we said, can be written in this form. It is our desired vector S transformed by this matrix R, and the noise also has been transformed, and we have called it here the vector V. Now, this vector Y, we have started looking at it as a particular in a particular manner. Do you recall what name did we give to vector Y besides calling it this reduced dimensionality sufficient statistics? That is one name we gave to vector Y. Do you recall what is the other name that we gave to Y?
So match filter?
Correct. It is the single user match filter output. We have been calling it SUMF, single user match filter output. So this is nothing but our traditional receiver, where if we assume that R is an identity matrix, meaning that W is the orthonormal matrix, then all that we need to do is just obtain Y and then perform decisions on the vector Y. Now in CT509, we are allowing R to be non-identity matrix, and so we have said that there are several solutions. One is called the decorrelating solution, which is just multiplies Y with inverse of R. And that actually perfectly removes the interference, but maybe at the expense of a little bit of messing around with the noise vector V. And that is something that we will try to analyze, hopefully, in today's lecture. We have also seen this MMSE technique, which adds what is known as regularization term. It's a diagonal matrix that is added to R. A lot of the times, the exact expression of this diagonal matrix, which is inverse of these SNR values, may not be available. We may not know what the SNR levels are. And therefore, this diag of 1 over SNR values is not possible for us to do. In that case, the trick that is oftentimes used is to add this diagonal component regardless. We just make up some SNR levels, and then we get what is known as the MMSE solution. The benefit of MMSE over the decorrelating solution is that in case if R is ill-conditioned, meaning that the columns of R are either linearly dependent, or even if they are not linearly dependent, the angles between the columns of R is turning out to be small. If the angle between any two columns of R is 0, then R is not even invertible. But when it is not 0, but maybe it is some small value like 1 degree or 0.5 degree, then R technically is invertible, but the inverse has some really large values. It is known as ill-conditioned matrix R. And then our decorrelator probably doesn't work as well, because our numerical inverse operation itself has a lot of maybe numerical imprecision errors, or even if the inverse can be obtained accurately. I think this is what we will try to see when we do the analysis part today, is that there will be a noise enhancement problem, essentially because we are multiplying V with inverse of R, and inverse of R starts having some large values. Whereas if we do this regularization, then the inverse operation becomes more better conditioned. And in fact, some of the problems that are there with the MMSE don't apply as much. With the problems of decorrelating techniques kind of reduce in some sense. If SNR values are very large, suppose if gamma S is, let's say 100 or 1000, then you can see that this diagonal term tends to become 0, and the MMSE solution becomes very much like the decorrelating solution. So in the large SNR case, there is probably not a lot of reason to go with MMSE, unless if R is ill-conditioned, or if R is non-invertible. However, in the low SNR case, the MMSE actually does outperform the decorrelating detector. Now, the other thing is that if the SNR values are very low, then what happens is this diagonal matrix that we have added to R starts dominating R. And if you take the limit that SNR values become almost 0, then actually all that we are doing is this R plus dag of 1 over gamma S becomes just dag of 1 over gamma S, because compared to 1 over gamma S, 1 over SNR, R becomes very small. And in that case, this MMSE becomes same as what? Can anyone say that? In extreme low SNR case, when the second term here starts dominating the matrix R, then this equation 6 becomes conceptually similar to?
So it's just scaling by a number.
Correct. And that number is just the SNR for that particular element of Y. Right? Because if I ignore R, then inverse of dag of 1 over gamma S is going to be just dag of gamma S. And so I'm going to take the individual SNR values, and I'm going to multiply the corresponding element of Y with the SNR corresponding to that element of Y. Okay, now one thing that I don't know if we have talked about it in CT516 or not, is that if I take this vector Y, the single user mesh filter output, and if I scale it, then it has no effect on the receiver performance. And the main reason is that the scaling, if I scale Y with gamma S, then that scaling affects both the signal component of Y and the noise component of Y in identical manner. The signal power goes up by the same amount as the noise power. And so effectively in the Q function, which has square root of signal power divided by noise power, the signal power and the noise power, when they both get scaled by the same constant, the ratio remains identical. And so this extreme case where we can even neglect R and we can think of MMSE as just performing diag of 1 over gamma S inverse operation on Y, then the MMSE becomes same as the SUMF. Okay, so the MMSE is kind of on one extreme, it starts approximating the SUMF. On the other extreme, it starts approximating decorrelating detector. Right? When signal to noise ratios are very high, MMSE and decorrelator become the same. When signal to noise ratios are very small, then the MMSE and SUMF become identical. But for all the intermediate cases of SNR values, MMSE always outperforms either the decorrelator or the SUMF. So that is the advantage of MMSE. The only requirement that MMSE has compared to decorrelation is that we need to know this gamma of S. Only when gamma of S are known perfectly, then MMSE outperforms both SUMF and decorrelation. But if you don't know the gamma of S, and as I said, if we do some trick, we just make up some gamma of S for the sake of regularizing this inverse operation, then we cannot be sure that the MMSE will outperform the decorrelation. Okay, so with that, we looked at several applications. One was this offline design of Beamformer, where we were able to take the system problem, the specifications of beamforming design, and we were able to write it in a linear algebraic manner, which is equivalent to that equation 2 on first slide. And from that, we were able to apply either the decorrelation technique or the MMSE technique for deriving the beamforming filter weights. In this case, we don't know the SNR values, and so we can put this small delta term, and this would be now known as a regularization operation. Again, if we make delta to be very high, then MMSE will become same as SUMF. If you make delta to be 0, then it will turn into decorrelation. We looked at another application, which is this code division multiple access. And we formulated the model of the received signal Y of t at the input to the CDMA receiver in this equation 8. Here there are a total of k simultaneous users, and we are assuming that their symbols B of k as well as their signature sequences S of k have unit energy. Viewed as vectors, these are unit length vectors. And we are considering what is known as synchronous model, where all of these k users are being received in a synchronous manner. So we are considering only one symbol interval. And that we looked at visualizations of this CDMA received signal model. And we were able to write, again, even for CDMA, we were able to write the received signal Y of t as this matrix vector product. Matrix has become this matrix of signature sequences. For the sake of notational clarity, we introduce the amplitude values as a separate diagonal matrix. and we kept the symbols as unit energy symbol vector in this vector B. Okay, so that is how we modeled the input at the CDMA receiver. And we formulated the correlation matrix among the signature sequences as R given as same as what we have defined R earlier, the transpose of S with S itself. And then we said that we can analogously apply either the decorrelation or the MMSE, or if you want, we can just go with this SUMF vector Z directly. In the initial days of CDMA, a lot of the receivers didn't want to do this inverse operation. And so some of the initial simpler implementations of CDMA receiver were just going by with the SUMF output Z. Today, given that we have more powerful FPGAs and processing abilities, typically either the decorrelation or the MMSE techniques are used for the CDMA reception. And we will see the performance advantage that we can get by doing either the decorrelation or MMSE as compared to the SUMF. Okay. Now, I want to consider a few more applications today before we jump into some analytical work. And one application is the Mimo reception. And here, the vector Y, now it is not a continuous time signal Y of t. Instead of that, I have called it vector Y. Can also be written in a manner which is very much like what we have seen earlier for the CDMA. All the continuous time signals became vectors now. Instead of different users having different symbols B of k, we are now having different antennas transmitting different symbols B of k. And there are a total of NT different transmit antennas. And so they collectively together transmit NT different symbols simultaneously in a synchronous manner. The signature sequences that we had for CDMA are now replaced by what is known as this channel vector H of k. And this H of k is an NR cross 1 vector, where NR is the number of receiver antenna array elements. Okay, so this H of k has taken place of Sk of t in the CDMA. Now, we can similarly normalize the channel vector to have unit norm. A lot of the times in the Mimo scenario, especially when the channel vectors are not assumed to be deterministic, if it is a line of sight Mimo, then yes, H of k can be thought of as deterministic, but otherwise, this will have some fading terms. And whenever we talk about fading, we have to bring statistical viewpoint. And so we can't say that an individual realization of H of k will have unit norm. But now we will have to invoke expectation. And only we can say only in the expected sense that these different channel vectors have unit energy. Instantaneously, the channel vector may not have unit energy when the fading is present, but still we can normalize them so that averaged over a long time duration, these different channel vectors are unit length. And then we can say that the transmit symbol energy averaged again over a sufficiently long time duration will be square of A of k. Okay, here I think I made a mistake. This n of t should be vector u. I will correct this mistake because I just copied, pasted the prior slide for CDMA here. I think this is a oversight on my part. Now we will have to call that this noise vector u actually has is a zero min Gaussian with variance of unity. So if I take correlation matrix of u, I will get an identity matrix. And therefore, sigma times u has variance of sigma squared. Okay. And so now actually I can write the Mimo model also as y is equal to hs plus sigma u. Oh, sorry. My mistake. Now I'm going to actually a different application. Anyway, this equation 9 is very much similar to equation 8. And so I can apply the same techniques that we have listed here. Either the SUMF, decorrelation, or MMSE on this vector y. And now that correlation matrix R will be the cross correlations among H of K's. So Mimo reception also can be modeled in this manner. Finally, one more application is what is known as this deconvolution technique, where again the received vector y is modeled as h times s plus sigma times u. But now h is the convolution matrix. Okay, and so the deconvolution problem is to determine s given the knowledge of h. Okay, so we have seen that there are many different applications. In fact, there is one more application which is the channel estimation in case of OFDM systems, in case of MIMO, in case of even this orthogonal time frequency space modulation, etc., where our interest is to determine the channel coefficients, which can again be represented as this vector s. The vector s is now no longer the symbol vector, but it is the vector of channel coefficients. It turns out that in a scheme called non-blind estimation or pilot symbol assisted estimation of channel coefficients, which is very widely used in OFDM, in MIMO, etc. The problem formulation is similar to equation 10. And so even for such a different problem of channel estimation, we can still apply the same techniques of either SUMF or decorrelation or MMSE. So that is one another application that I have not included here explicitly, but maybe I will do that before our next lecture. As we went over this several different applications, we could see kind of a common structure or a common theme in where we can write our received vector r as h times s plus u. Sometimes we brought this diagonal matrix of amplitudes of different user as a separate matrix. A lot of the times we absorb that amplitude matrix into this vector s. But apart from that detail, in all of these different applications, we could write the vector r as this linear algebraic equation. And now our goal is that when we have measured this vector r, and if we know h, and if we assume that its columns are linearly independent, how to determine the vector s. and that the solution of the three solutions of that problem is what we have seen: the SUMF, the decorrelation, and the MMSE. Okay, so those are the three solutions here. I mean, two solutions. The SUMF is just H Hermitian R, which is this vector Y of sufficient statistics. I should actually explicitly write the SUMF as the first solution, the most simplest of all. Okay, so that is kind of a unified treatment of many different problem domains. Now, let us get a little bit into the mathematical analysis now of these different techniques. And actually, before we jump into the detailed mathematical analysis, maybe we will also look at some computationally efficient schemes for implementing either the decorrelation or sometimes even the MMSE. Okay. For the analysis, I think our focus will be on CDMA. The reason I want to keep the focus on CDMA, although as we have seen, pretty much the entire analysis that we'll be doing in terms of CDMA can be extended to these other application areas as well, given that unified model that we just now saw. Here, my viewpoint is going to be CDMA because pretty soon, maybe either as soon as starting next lecture, or if not next lecture, definitely immediately after your exams next week, we are going to do kind of a change in our topic, and we'll be focusing a lot then on the non-orthogonal multiple access, NOMA. And particular realization of NOMA uses CDMA technique. So understanding CDMA receivers and their performance in a conceptual manner will allow us to kind of get a better feel of NOMA as well. Okay, so at the CDMA receiver, when we do this operation, remember this is what we are calling the SUMF operation. I want to look at the vector that we get at the output of SUMF of the noise component only. And so that vector, we have called it to be this vector U. It's a k-dimensional vector because this S has total of k columns. Effectively, we are projecting the received noise vector onto k columns of S. And accordingly, we get the k projection values which are captured in this vector U. Now, I want to ask you, if I take the correlation matrix of N, what will that be?
Diagonal.
Right. So we have assumed N to be the white noise signal. Basically, it's uncorrelated. And so if I take N of T times N of T conjugate transpose, then I get not only the diagonal matrix, but I get the identity matrix. If I take correlation of sigma times N of T, then I get a scaled identity matrix where the scaling is sigma squared. Okay, now given that, I would like you to derive the correlation matrix of R of U. Basically, derive the correlation matrix RUU. You may need pen and paper, but it's pretty straightforward if you just work out the math, especially given that the correlation matrix of n of t is going to be identity matrix. The correlation matrix of u should be pretty straightforward for you to derive.
Sigma square S Hermitian S.
Correct. But I would like you to further simplify that. I mean, it's already simplified, but I would like you to tell me more compact version of the answer you gave.
Sigma square expectation of R.
Right.
Yeah.
But R is already expectation because it's correlation matrix. Right? In fact, we don't do expectation because we assume that S of t are deterministic. But the point that Divya makes is correct. It is just sigma square R. So let us see that here. I think those of you who did the math, you would have done something like this. This matrix S is deterministic matrix, so I can bring it outside of the expectation operation. This matrix, as we said, is the identity matrix, so it goes away. And so what I get is what Bhavesh said, sigma square S Hermitian S. But that is how we define the matrix R, remember? This is the correlation matrix of the signature sequences. And so the correlation matrix of U is nothing but sigma square R. Now, in general, R is not a diagonal matrix. And so what we can say is that unlike the noise vector at the input to the SUMF, at the output, if I take the noise at the SUMF for user 1, and if I consider it in relation to the noise at the SUMF of user 2, then the correlation between them is not going to be zero. It will be determined by the element on the first row and the second column of R. Right? So basically, the noise at the output of SUMF is not white anymore. It is not having zero cross correlations. In the literature, sometimes this is known as coloring of the noise. This vector U is colored noise. It is not white noise. And the coloring means that the correlation matrix of R, correlation matrix RUU is not just the diagonal matrix anymore. Okay.
Sir, what will be the dimension of R?
We have done this before. What is the dimension of R? Who can tell me?
A cross K?
Sorry?
K cross K?
K cross K, yes. Where K is the number of users. Because this S matrix has total of K columns. Total of K columns. Because there are K users. And each user has a specific signature sequence. And so this S has dimensions of some N cross K. So correlation matrix is always K cross K. Even for the very first model that we had used, this R was K cross K. Essentially, we are denoting the number of the dimensions of this vector X to be capital N, and the dimension of this vector S to be capital K. There are K users and they are being observed over an n-dimensional vector in all of these different problem formulations. And typically we make this n to be greater than capital K. If it is compressed sensing, actually it is the other way around. N is smaller than K. But as of now, we are not talking about compressed sensing. So typically N is greater than K. And then this correlation matrix is K dimensional.
So for the single user match filter, R is a scalar, right?
Correct.
Okay.
So for single user mesh filter, R is not only a scalar, it is just 1. The reason it is 1 is, remember, we have said that S is normalized to have unit energy. So if I do the dot product of S with itself, it will be 1. So if it is a single user mesh filter, I get, sorry, what am I talking about? If capital K is 1, then I get back to CT516 formulation when there are no interferers, when there are no such simultaneous K sources present. And then SUMF is optimal. It gives me the maximum likelihood or the map result. Okay, now this coloring is sometimes a problem. Not only in terms of if you want to understand and analyze the performance of the receiver, but sometimes it's a problem even when we are trying to do some advanced algorithms. One such algorithm is called decision feedback estimation. Maybe we'll get into decision feedback scheme later on. It is not considered as a linear scheme. The three linear schemes are pretty much all that are ever considered: SUMF, decorrelation, and MMSE. If we have some additional computational power, and if you want to further improve upon the performance of the linear scheme, then we get into non-linear schemes. And one such non-linear scheme is called the decision feedback algorithm. And in the design of the decision feedback algorithm, sometimes it is useful to have the input where the correlation matrix of the noise is not colored. And so there, an advanced technique is to do what is known as Cholesky Factorization. Maybe in your linear algebra course, you may have studied Cholesky Factorization. If not, then just a very one bullet summary of Cholesky Factorization is that it can take this matrix R, the correlation matrix R of the signature sequences, and it can factorize it as this product F Hermitian F. And where F is a lower triangular matrix, and therefore F Hermitian is the upper triangular matrix. This is sometimes also known as square root factorization of R. The reason it's called square root is because R is being considered as a product of matrix F with itself after this transposition. In fact, we can almost think of R as square of F, where the squaring is done after Hermitian transposition. And so, yeah, Joel said PCA also decorrelates the data. That is correct, Joel. But Right now, PCA is not within our scope, although it's a very good technique to understand. Maybe let's not focus on PCA right now. By the way, Joel has written a nice tutorial introduction on the principal component analysis. So what I'll try to do is, as a reference material, I'll put that tutorial on our Google Classroom. Okay, so this PCA is kind of an application of eigen decomposition, and it's good to understand that technique in general. But right now, let us continue with this Cholesky scheme. So what is done is, in the Cholesky processed method, we take the SUMF output vector, which we have seen earlier. It can be written as Z is equal to R times A times B plus sigma U. And we multiply it with inverse of F Hermitian. Okay. So let us call the result as Z cap. So Z cap is F Hermitian inverse times Z. But Z is this R, A, B, sigma U, and R is F Hermitian F. So I get the second line here. And now F Hermitian inverse F Hermitian cancels out, and so I get FAB plus U cap, where U cap is F Hermitian inverse times U. Now, who can tell me the correlation matrix of U cap? What will it be? Remember, you already know the correlation matrix of U. All I want you to do is determine the correlation matrix of U cap, which is defined as inverse of F Hermitian times U.
Inverse of F into F Hermitian into F inverse. Sir?
Yeah.
F inverse Hermitian into F inverse.
No.
U
The correlation matrix of U cap will be what? Actually, the subtitle of this slide already gives you a hint.
diagonal.
Yes.
Right identity.
Sigma
Yeah,
square.
Sigma
Sigma
correct.
square into identity.
Correct. So it's going to be a identity matrix scaled by sigma square. Why is that the case? Oh, okay. I didn't write it explicitly here, but it looks like Divya has done it. Those of you who have not done it, you can take it that if you do the calculations, which are not difficult, you will see that the correlation matrix of U hat is sigma square times identity matrix. And so effectively, U hat is now back to this uncorrelated noise vector. And therefore, this F Hermitian inverse times Z is called the whitening transformation. And this decision feedback is sometimes done on the whitened Z cap instead of colored Z. Okay, so that is something that we should mention here. So something that is kind of one of the central pillars of linear algebra, we are able to leverage that here. One other application of this Cholesky is that when the problem is very large, it actually is a computationally attractive scheme, because we don't need to take inverse of R if we rely on Cholesky technique. And so let us see that. Here, basically, the triangular nature of F is leveraged. The objective here is not to decolor the noise, but rather to simplify the computation, basically avoid the inverse of R that is needed for decorrelation. So remember that our estimated vector B hat is R inverse Z. And so obviously I can write it as R B cap is equal to Z. But remember, R through the Cholesky factorization, I can write it as F Hermitian F. So now the trick that I'm going to play is I'm going to call this F times B hat to be B hat tilde. And so now I got this equation, F Hermitian B hat tilde is equal to Z. But F Hermitian is a triangular matrix. And whenever we are dealing with this type of linear algebraic equation where this matrix is triangular, we can solve this without doing inverse. And so this F Hermitian B hat, sorry, here I have a typo. This should be B hat tilde, the last equation. So we can solve this triangular system without doing any inverse, right? Because in this upper triangular matrix F Hermitian, if I look at the lowest row, the last row of F Hermitian, it has only one non-zero element. All others are zero. And so I can just look up the last element of B cap tilde as the last element of Z. And then I keep on doing back substitutions. I already know the last element of B cap. So I can get the previous to the last element of B cap, because the previous to the last row of F Hermitian will have two non-zero values, one corresponding to the element that I have already determined, and the other is the unknown element. Right? So I can just do the back substitution starting from the last row all the way up to the first row. And each time when I go to a row, I would have determined all of the unknown variables except only one. And so I'm not doing any matrix inverse here at all. So by solving this upper triangular system, I got B hat tilde, but B hat tilde is another triangular system. B hat tilde is F B hat. Now remember, I know B hat tilde because I had solved it in this first step. F is again a triangular matrix. And so I can again apply the this back substitution scheme, except now I'll be able to determine the first element of B hat first, because it is the first row of F which has only one non-zero. So I'll go from the first row to the second to the third all the way down to the bottom, and I will have determined B hat. So we see that the matrix inverse was not needed. I could still do the decorrelation, but without doing explicit matrix inverse. What I still needed to do was this Cholesky factorization. Okay. Now, I mean, while we are on the topic of this numerical optimization of either the decorrelator or even the MMSE, I want to look at one other method which is called singular value decomposition. Basically what it does is it takes the singular values of and singular vectors of S of t, the matrix S of t. And okay, now we come back to our main equation, R times B hat is equal to Z, but we take this S of t and consider it as this in the singular value decomposition manner. U, this sigma matrix, which is a diagonal matrix of singular values, and V Hermitian. Now, we haven't done singular value scheme in a whole lot of detail in this course. I'll be actually uploading a tutorial that is quite nicely written that you can study on your own. But basically, one key component of singular value decomposition is that both of these matrices U and V are orthonormal matrices. Their columns are orthogonal and they have unit norms. And this U is actually the U is obtained as the eigen decomposition of R. And V is obtained by eigen decomposition of R Hermitian transpose. So this U and V are nothing but the eigenvectors. U is the eigenvector of R and V is the eigenvectors of R Hermitian transpose. And because okay, I think I misspoke. So sorry, so V is actually the eigen decomposition, the eigenvector. V contains the eigenvectors of R and U contains the eigenvectors of R Hermitian transpose. Okay. So that is, I think, my little fuzziness on my part, but I can write R as in this eigen decomposition manner. And so now let us see where this power of SVD can be leveraged. This is the equation that we traditionally solve using R inverse. But instead of that, we write it like this because R has been written as in this eigen vector manner. S is already decomposed using the singular values. And so in the third line, I wrote S using the singular value decomposition. Okay, now what you will see in the third line is that there is a common matrix V, which is present on both the sides of this equality. So I can remove it. I can multiply by V transpose or V inverse, which is same as V Hermitian transpose. And so I get the fourth line. Now in fourth line, you will see that I can multiply both the sides by inverse of square of sigma. So I get the fifth line. And then finally I get sixth line because remember V is an orthonormal matrix. So I just multiply both the sides by V. V Hermitian is identity matrix. And so on this line I got this equation. So I'm able to get the B hat vector again by not requiring any matrix inverse as such, except this sigma inverse. But sigma is a diagonal matrix, and so its inverse is trivial. We just invert the elements. And so this is not computationally expensive operation at all. So the SVD, what it does is instead of doing the SUMF, actually it in fact, in SUMF, the received vector Y is projected on the signature vectors as K of T. There are a total of K vectors, and we project Y on each of those K vectors. So instead of doing that, in the SVD technique, we are doing this operation. So we are projecting Y on the columns of U matrix. And therefore we get this Z cap. Unlike S, columns of U are orthonormal. And so the Z cap that I get is a lot like what we get in CT516. The noise remains white. The noise is not getting correlated. And in case if the columns of S matched the columns of U, then I can stop here. I don't have to do any further processing. But in general, I will have to take this Z cap and now I will have to scale it by the inverses of singular values. So I get Z cap tilde. That still doesn't give me B cap because this is in the coordinate axis specified by this matrix U. My solution is in the coordinate axis specified by this matrix S. And so I will have to rotate the Z cap tilde. Here there should be a tilde sign on top of C cap. I will to rotate it by the vector V. Sorry, matrix V. And then I'll get the estimate B cap. So the decorrelation operation, I have converted that as projecting the input onto an orthonormal basis. The scaling operation after we do that projection. And then we rotate the scaled projected outputs by another orthonormal basis to get B cap. So projections and rotations and scaling is all that is needed. Matrix inverse is not needed here. And so this is again computationally friendly scheme. But the SVD scheme, in general, the eigen decomposition schemes are otherwise very elegant schemes, and they have a lot of far-reaching applications. And so I don't want you to think of SVD only as computationally friendly scheme of implementing the least squares or the decorrelation. The tutorial that I'll be posting shows the full scope of this SVD method. Okay, so I will take a brief pause here, and then we will resume in I'm going to skip over this part because we have done this last time. Okay. So now let us get into this receiver performance analysis. I forgot to put it on full screen mode earlier. Okay, so we'll start actually by analyzing the SUMF in the context of CDMA. And we have seen that the SUMF output is this vector Z. We also derived the correlation matrix of this vector as Hermitian transpose N of T, which we have called vector U. Actually, Divya already asked this question that if I have only one user, then what happens? So R becomes just a scalar. Only one element of R is present, and that element, because of the normalization of the signature sequences, is just one. And so the receiver measurements are obtained as A1, B1 plus U1. Now, suppose if we take that this symbol values are BPSK, then who can tell me what will be the probability of bit error? This is exactly the same model that we had studied in CT516.
So bit error rate was the Q function, no?
Yes.
So here it will, I mean, here the rho 11 term will be sigma square into 1. So, and bit error rate was Q of sigma square upon D. I don't know the D.
So when the receiver decision statistic can be written as A times B plus U, where B is either 1 or minus 1, and U has a variance of sigma square, what is the mathematical expression for the probability of bit error?
Sigma square upon 2B1, 2B. Q function of that.
No?
So Q root EB by sigma square.
EB क्या है लेकिन मतलब ऐसे एनर्जी बोलेंगे क्या A1 के टर्म्स में नहीं बोलेंगे.
Yeah. So Arushi said a Q of square root of 2 times SNR. Anudeep is saying 2 times N naught, but we have not defined SNR, we have not defined N naught. What I want you to do is think of, first of all, what will be the decision boundary? When will I decide after receiving Z, when will I decide that B1 is 1 versus B1 is minus 1 or 0?
B1 by 2?
The decision boundary is at?
0, sir.
0, sorry, 0. It is minus 1.
0.
Sir, it will take values minus A1 and plus A1.
Correct. So the values presence of noise will be minus A1 and plus A1. In presence of noise, there will be a bell-shaped PDF. And whenever that PDF goes on the other side of 0, that is where the error will happen. So the bit error probability is the integration of the PDF on the wrong side of the decision boundary. It is given as Q function of. The answer is dependent only on A1 and sigma.
Sigma square upon 2A1. Q of sigma square upon 2A1.
Okay, no. I think you got it inverted.
Q function of, Q function
D
of
upon
square root
sigma
of
square.
2A1
Sorry.
upon sigma square.
Yeah, except that 2 comes only if you are talking about EB over N naught, because sigma square is N naught divided by 2. Yeah, so I think Joel got it right. It is going to be Q function of A1 divided by sigma. A1 is the mean of the Gaussian PDF. Sigma is the standard deviation of Gaussian PDF. And we are evaluating the area under that Gaussian PDF, which goes on the other side of the decision boundary. And that is just Q function of A1 divided by sigma. So the SUMF for the case of a single user is derived here. Now let us consider the case of 2 users. And we'll still keep on working with the BPSK modulation. So we will have B1 and B2, which are +1s and -1s. Now for 2 by 2 case, the R matrix looks like this. Remember, R is Hermitian symmetric. And specifically for CDMA, actually it is just symmetric, because the signature sequences typically, although not always, typically they are real valued. Remember, we saw one example of signature sequence which was just a rectangular waveform. You see that either ones or -1s. So in a lot of cases, the signature sequences are real valued, so the correlation values are all real. And in that case, it becomes just a symmetric matrix. If otherwise, it will be Hermitian symmetric, or basically what is known as Hermitian matrix. And remember that we are forming, for the SUMF, we are forming this vector Z, which is R times A times B plus the noise vector U. So now let us look at what is happening with the Z1. Okay, so we are looking at Z1. Over here also we looked at Z1, but here Z1 was very simple, A1, B1 plus U1. In this case, because R is not a diagonal matrix, it is this matrix, what will be Z1?
So can you repeat the
Okay.
No, I'm just asking that for the single user case, we already looked at Z1. It was just A1, B1 plus U1. For the user case, what will be the expression of Z1? I mean, all you have to do is just look at the equation. R is given by this.
Oh, okay.
Sir, it will be A1 plus rho plus U1.
A1, B1 plus?
Rho A2, B2
Yes.
plus U1.
Plus U1. Correct. So The decision statistic is same as before, A1, B1 plus U1, but now there is this A2, B2 times rho term coming in. This is the interference from the second user as it appears on the first user's SUMF output. And this rho, which is the cross correlation between the signature sequences of the two users, determines the amount of interference. And the other part which determines the amount of interference is A2. Okay, now let us see two cases. Okay, so we already saw that if this middle term was not present, the error probability is going to be Q function of A1 divided by sigma. Now, we have this interference term present here, and therefore the error probability is not going to be simply Q function of A1 divided by sigma that we did here. It's not going to remain this anymore. So let us consider two cases. One in which, remember, B2 is BPSK. So let us assume that this user 2 has transmitted BPSK symbol of 1. In that case, what will be the error probability for user 1? Given B2 is 1, what is the error probability for user 1?
Sir,
Sir, same as previous one.
Probably is not same because there
so
is this
this one is
interference term.
also the noise, right? A2, B2 will also act as a part
No,
of noise only
A2
for the
is the
first
amplitude.
signal.
Okay. No, Bhavesh, A2 is the amplitude. It's a fixed value. It's not a random value. So we think of A1 and A2 as fixed. They're constants. Once you start transmitting at certain power, that is where you keep on transmitting. So the receiver will not see fluctuations in A1 and A2.
Right, sir. So, but we can
Rho
see
is also a
fluctuation.
constant.
Okay.
The only variable is U1, but U1 is just the noise. So remember we said here that the way we get this answer is by thinking of the decision statistic as having a mean of A1. Suppose B1 is 1, then the mean is A1. And around that mean, there will be a bell-shaped PDF because of the zero mean U1. And the standard deviation will be sigma. And the error probability is A1 divided by sigma, Q function of A1 divided by sigma. So that is how you want to think about this problem also. What will be the mean and what will be the standard deviation of this Z1 when suppose B1 is 1? And we are assuming that B2 is also 1. What will be the mean of Z1?
A1 plus A2.
2 rho by 2. A1 plus A2 rho by 2.
A1 plus A2 rho by 2. Why divide by 2? I'm saying that B1 equal to 1 has been transmitted. So there are 4 possibilities.
A1 by 2.
Yeah. Okay. So So Anudeep gave the answer, and I think Arushi also said the same thing. Basically, first of all, we are fixing B2 to be 1. And now we are trying to determine the error probability. That probability for the case when B1 is also 1 will be given by a Gaussian PDF whose mean is A1 plus A2 row. What will be the standard deviation? It will be the standard deviation of U1. So no. Anudeep, remember all of this, the first two terms are constants. They are not variables. Because I am fixing B2 to be 1, I am fixing B1 to be 1. A1 and A2 are related to power, so they don't add to the standard deviation. The standard deviation is coming only from the Gaussian noise. So the case when B1 and B2 both are 1, the error probability becomes the mean has become A1 plus A2 row. The standard deviation is still sigma. And so the error probability is
A1 plus A2 rho by sigma, Q function of
Q
yes.
of that term.
Right? So instead of just A1 divided by sigma, I get A1 plus A2 rho divided by sigma. Now, this sigma is correlation value, and let us assume again, for the sake of simplicity, that in general, this correlation value will be any value from -1 to 1. Specifically, this correlation can become negative also. But for the sake of simplicity, let us assume that correlation is greater than 0. It's positive. Then what is going to happen is, in this equation that we had, instead of just A1 divided by sigma, I got A1 plus A2 rho divided by sigma. And remember, A1 is magnitude, it is never negative, A2 is also never negative. We have assumed that this rho is also positive. So A1 plus A2 rho divided by sigma is going to be bigger than A1 rho divided by sigma. When the argument of Q function becomes bigger, what happens to the value of Q function?
it decreases.
Decreases. So actually in this case, what we are finding is, surprisingly, when both the users are transmitting the same bit +1, the error probability actually goes down. We did the case when B1 is 1 and B2 is 1. If we do a similar case where B1 is -1 and B2 is also -1, you will also get the same answer. You can do it yourself. The PDF, the conditional PDF, instead of being centered at A1 plus A2 row, instead of that, it will be centered at -A1 minus A2 row. It will go on the negative real axis. But the problem is symmetric. When it is centered on the positive real axis, we are trying to find out the area under the PDF which falls on the negative real axis, on the left-hand side of Z1 equal to 0. That is when B1 and B2 are 1. When B1 and B2 both are -1, the conditional PDF becomes the mirror image. It is centered at -A1 minus A2 row. But now we are trying to find the area under that Gaussian PDF on the positive real axis on the right hand side of z1 equal to 0. And so the expression for the error probability remains same, q function of a1 plus a2 rho divided by sigma. So actually, when both of the users are transmitting the same values of the symbol, compared to the single user case, this two user case actually works better. Effectively, the signal to noise ratio goes up. Now I want to ask you, what happens when B1 is 1 but B2 is minus 1? What will be the error probability in that case?
So A1 minus A2 rho Q.
Yes.
I mean, that.
Yes. So now we are going to get hurt. Compared to this expression, A1 minus A2 rho will be smaller. And that expression which Bhavesh just now said will be applicable for the other case as well, where B1 is minus 1 and B2 is 1. So we have four cases of B1, B2. 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1. For the first and the fourth case, 1, 1 and minus 1, minus 1, the error probability is given by this expression. A1 plus A2 rho divided by sigma. Those are the two cases. Both of the cases have probability of 1 over 4. And so if I add up, I get 1/2. This is the good case for me. But unfortunately, I have this bad case when B1 and B2 take opposite symbols. And there are two possibilities there as well. Minus 1, 1 and 1 minus 1. Both of them have a probability of 1/4. So if I add up, I get this first term. The problem comes because my error probability is going to be dominated by this term. Let us take some specific values that this, let's say, q function of a1 divided by sigma is, let us say, 1%. So if it was just one user, I get probability of error of 1%. This term here, let us say it became better and that 1% became 0.1%. And so now when I divide by 2, I get 0.05%. So this term is contributing 0.05% to the overall error probability. But what about this? Let us say that because I'm subtracting the numerator by A2 rho, that A1 divided by rho, which was giving me 1%, now it became 10%. So the overall probability is going to be 5% from here and 0.5% from here, 5.5%. And so I can almost ignore this second term because it is going to be smaller compared to the first term. So I can almost say that my performance is going to be given as this Q function. So maybe there should be 1/2 multiplier here. But what I'm doing is I'm upper bounding this. So technically I should multiply this Q function by 0.5, but that value will be definitely lower than if I don't multiply by 0.5. So if I'm interested in upper bounding, I can say this is definitely an upper bound. The actual value, which is 1/2 times this, is going to be lower than this. So the SUMF performance will always be better than this Q function. Not a whole lot better, actually. Remember, we got 5% from here, 0.5% from here, and I am bounding the result 5 plus 4.5, 5.5 as 10. So this 10% answer that I got from by taking this Q function is an upper bound, and the actual value of 5.5 is kind of similar to 10. Instead of 10, if I say 0.01%, then my bounding is pretty bad. Or if I say 50%, then also my bounding is pretty bad. But here I'm pretty much bounding it by twice of this term. The point is that the overall performance of the SUMF is going to be determined by A1 minus A2 magnitude of rho divided by sigma. So here I have magnitude of rho. Basically, it is as if the rho is just positive valued. Okay, now let us do some thought experiments. And let us assume that A1 is less than A2 times magnitude of rho. And let us even ignore the noise entirely. Remember, if noise is not present, if it was just the standard single user case, if I took this rho to be nearly 0, then this argument of Q function will become nearly infinity, and therefore the answer will be nearly 0. Q function will be 0. Basically, in absence of noise, the receiver will not make any error whatsoever. The probability of error will become 0. Now I'm asking, in this case, let us say U1 is not present, so it's a noiseless case. And I'm saying that A2 times rho is bigger than A1. It can happen. Let's say rho is 0.1, A1 is 1 and A2 is 20. Or, yeah, so A1 is 1 and A2 is any value more than 10. If A2 is 20, 20 times 0.1 will be 2. 2 is definitely bigger than A1. So I'm asking you to consider what will be the behavior of the receiver in this case. Basically, what will be the probability of errors? You don't even have to bring Q function or anything here. We just look at this equation and say if U1 is 0, A2 rho is bigger than A1, and then consider 4 possibilities of B1 and B2.
So in two cases, it will be very good. In two cases, when B1, B2 are either both positive or both negative, it is good. It is very good. But in the other case, the opposite case, it completely fails because
Correct.
it will go on the other side. Yeah.
Correct. Which means that we will be always making an error because it goes on the other side, whenever these signs are different, B1 and B2 signs are different. But that happens with probability of 0.5. Out of 4 cases, half of the cases are those problematic cases. And so the probability of error becomes 50%, which is useless. 50% is, you can't work with it. So this is the problem of SUMF. In practical cases, when this will happen is when user 1 is far away from the base station. Maybe it is at the edge of the cell. And user 2 is like sitting very close to the base station. Unfortunately or fortunately, whichever way you want to think about it, 2 years back, I don't know who, maybe Jio or Vodafone, they put up a big cell phone tower right next to my house. So in the context of SUMF, I am this lucky user too. My values will be like A2. But if I go to our college campus and if my phone is still connected to the same tower, which it most likely is because the phones are kind of latched on to a particular tower, then I would be like user 1 because I am like 3 kilometers away from that tower. So this type of situation happens all the time. That there are 2 users, one user is very close to the tower, and so A2 is much greater than A1. And so now, even if this row, the correlation between the signature sequences is pretty low, if A2 overcomes that attenuation introduced by the correlation coefficient row, we will have a problem. And this is called the near-far problem. The nearer receiver will destroy the performance of the far away receiver at the SUMF. Even in absence of noise, even when for some reason the base station equipments are very nicely designed so that the thermal noise is very small, even in that case, it's this other user which is situated closer to the tower is going to destroy the performance of a user which is far away. Okay, we will spend maybe another five or so minutes and try to complete this as much as possible. So this is, okay, fine. So here we assume that when the noise is small, what happens? But otherwise also, we can say that because our performance is going to be pretty much determined by this term here, it is as if our SNR reduced from A1 square divided by sigma square to A1 minus A2 rho whole square divided by sigma square. And when A2 times rho starts becoming similar to A1, then you can see that SNR starts becoming smaller. In the case when both of them are same, then the SNR actually becomes 0. You need 2 different things. One is that rho should be very small. And secondly, not only that rho should be small, A2 should be smaller in comparison to A1. And you can't guarantee that because the users will be situated anywhere within the cell. And so for some users, at least, this SUMF is going to have at least a reduction in SNR. If not this worst case situation when the noise is not even present, still you get 50% errors. Let us now see what happens if we do decorrelation. Remember, the decorrelation output is written as B hat is equal to A times B plus R inverse U. If you want to go back to that, let us see why that is the case. Apparently, I never wrote it down in specific, but this is the SUMF. If I multiply by R inverse, I get A times B, because R times R inverse cancels out. So B hat, which is R inverse Z, becomes A times B plus R inverse of U, which we have already analyzed at the start of this lecture, which is this actually. It's, the correlation matrix becomes sigma square R. Okay, so this R inverse U is denoted here as V. Maybe we used a different notation earlier on. But the correlation matrix of V is sigma square R. And therefore, if I do R inverse of U, basically if I take correlation matrix of V, I get sigma square R inverse. So on page 99, we had, at the start of today's lecture, we derived this equality, which I have used here. So RVV is sigma square R inverse. Now, let us see the decision statistic for user 1. Now, remember, this is the only equation here. A is a diagonal matrix and there is a noise term V. And V has this correlation structure. And so there is no A2, B2 term at all here. It's just A1, B1 plus V1. It's almost like as if it was single user match filter in the ideal case of only one user present, except now the variance of V is going to be given by sigma square R inverse. But R for the two user case, we have already said it is one row, row one. And so if I do R inverse, sorry, actually there should be an inverse sign in front. If I do R inverse, I get this matrix. It has 1 over 1 minus rho squared and then 1 minus rho 1. This is the inverse of R. The variance of V1 is going to be determined by the first element here, which is 1 over 1 minus rho squared. Plus there was this sigma square term also. And so variance of V1 is sigma square divided by 1 minus rho square. And so now I can use the same expression as before, except A1 divided by sigma has to be replaced by A1 divided by sigma square root of 1 minus rho square. Basically, square root of this term. Does this make sense? How we got here?
So can you repeat the third point?
Okay, we are looking at decorrelating detector performance. And for decorrelating detector, the interference is not present at all. B hat is just A times B plus V. That R matrix has gone away in the A times B term. R matrix is present in V. And therefore, the covariance of V is sigma square R inverse. And so if I look at the decision statistic for first user, because the interference from the second user is not present, it is just A1, B1 plus the noise term V1. But the variance of V1 we have already determined here. It is going to be given by the first element on the diagonal of RVV. That is how we define the variance of V1, the first element of V1. So all we need to do is to look at what is the value of first element of this matrix. I mean, what is the value of the first diagonal element? The element at the first row and first column of RVV. For the two-user case, because R inverse takes this particular form, there is a typo here, it should be R inverse. The variance of V1 is going to be given by sigma square over 1 minus rho square. And so this equation here is otherwise identical to this equation. Only thing has happened is U1 has become V1. And so we expect the probability of error to be having the same expression as this, Q of A1 divided by the variance of the noise. But the variance of noise has now become the original variance divided by 1 minus rho square. And so this is the probability of bit error. Does it make sense?
Yes, sir. Please now.
Okay. Now remember, rho takes value from -1 to 1. And so whenever rho is going to have small values, it is okay, it is not a big deal. If rho is like 0.01, then 1 minus square of 0.01 is almost same as 1. And I'm going to get a performance which is nearly same as if there was just one user present. But when rho becomes bigger, then this noise gets amplified. Sigma square becomes bigger. If rho square is 0.5, then my noise variance goes up by a factor of 2. Because 1 minus 0.5 is 0.5. Sigma square divided by 0.5 is 2 times sigma square. And so although I am removing the interference, specifically the performance is not dependent on A2. The near far problem is gone. The performance now still is dependent on the correlation coefficients. If two different column vectors of this matrix, signature sequence matrix, if they are highly correlated, then because of that correlation, the overall SNR deteriorates and the performance becomes worse. So we never get the type of strange situation that we had seen earlier for the single user match filter, that even in the absence of noise, we can get error probabilities which are 50% because of this near far effect. That situation doesn't happen. But we still have to be careful. We can still get hit quite significantly. Our performance can still take a big hit if these rho values are not very close to 0. Okay, so we will stop here.